Hello everybody, you're watching JustWilhelm, and today I'm going to be doing a video about stars. This is just a one-off video, it's not going to become a countdown channel. I don't have anything against countdown channels, by the way, just in case you thought I did. I'd like to share this video because I'm interested in astronomy myself. If you're not interested in astronomy, then you probably won't know what I'm talking about for the whole video. But if you are interested in astronomy, I highly recommend watching it because I think you'll enjoy it. I'm also using slightly different terminology for some things, so just so you know, when I use the term compactor, I'm referring to a white dwarf star, and when I use the term planetar, I'm referring to a brown dwarf. Also, because I'm special, I'm using luminosity class 2 as supergiant and luminosity class 1 as hypergiant, and I'm not using the bright giant class. Spica. The brightest star in the constellation Virgo has a secret. It is a binary of two B-type stars so close to each other that they're distorted by each other's gravity. They also have rapid spinning rates and are both on the borderline of O class. However, the secondary will still become a compactor at the end of its life. The primary, on the other hand, is right on the borderline of producing a neutron star at the end of its life, though it still may become a compactor. Spica A is also a variable star. Its outer layers regularly contract and expand, meaning that the diameter of the star is not constant. Spica B's light is occasionally scattered by the primary's strong stellar wind. Fomalhaut. Fomalhaut, a system with 3 stars, 2 of which have dust disks, is the third brightest star with the planetary system, visible from the Earth after the Sun and Pollux. Fomalhaut A, or just Fomalhaut, is a young A-type main sequence star that is orbited by multiple belts of gas and dust, and by a large planet named Dagon, the first ever exoplanet to be directly imaged. Some observations also suggest a second planetary body. Perplexingly, the disk around Fomalhaut A, believed to be a planet-forming region, is off-centre to the star. Fomalhaut A is also rotating rapidly, at 93 km per second. Fomalhaut A is also accompanied by the variable K-class star TW Piscis Austrinae, Fomalhaut B, at a distance of 0.91 light-years, and by an M-class star LP 876-10, Fomalhaut C, at a distance of 3.2 light-years. This red dwarf star is also surrounded by a debris disk, which also harbours planet formation. If intelligent life does develop in this system, it will on Fomalhaut C, as the star's lifespan is long enough to support evolution of complex life. As the 3 stars are so widespread, the tidal radius of the system extends to 6.2 light-years. Algol. Algol is a system of many stars. The system is dominated by 3 bright stars, a B-type star, a K-type subgiant, and an A-type star, along with a collection of fainter companions. The seemingly impossible central pair, Algol A, consists of a hot B-type main sequence star and a cooler K-type subgiant. The fact that the less massive star is more highly evolved is not naturally occurring, and leads to the question of the Algol paradox. This phenomenon can be explained by mass transfer between Algol AA and AB. Originally, AB will have been the more massive star, but as it expanded into the subgiant stage, gas spilled onto Algol AA, causing it to gain mass and become hotter over time. Today, this process is still underway, leaving us with a more massive and smaller primary, and a less massive, cooler and larger secondary. Algol passed within 9.8 light-years of the solar system around 7.3 million years ago, potentially perturbing the comets of the Oort cloud. Almaz. Almaz is a unique large-scale system of an F-type supergiant and 2 main sequence B-type stars surrounded by a thick disk of gas. The mass of the supergiant primary is either considered to be intermediate or high mass. In the intermediate mass scenario, 2.2 solar masses, the primary has lost mass to the binary secondary, partially forming the disk, a mechanism similar to that observed in the Algol system. Alternatively, Algol A is still a high-mass star, a more feasible explanation regarding luminosity measurements. This, however, means that another explanation will have to be created for the disk surrounding Algol B. Algol B is believed to be a close binary of two B-type main sequence stars with a total mass adding up to about 6 to 14 solar masses, 3.7 solar masses for each component assuming they are of equal mass. This means that Algol B itself may also have an eventful future, potentially including Algol-type mass transfer depending on the initial mass difference of the two components. Hatzaya, Mu Columbi, AE Aquarii, the Flaming Star Nebula, and 53 Eritis. Yes, I know, these are 4 star systems taking up one place on the countdown. I know, it's not exactly a top 10 anymore, but it never really was because of multiple star systems. Mu Columbi, AE Aquarii, and 53 Eritis are all runaway stars, stars that travel through space with a high velocity, that have been traced back to the heart of the Orion Nebula and the star system Hatzaya, also known as Iota Orionis. Now in the constellation Columba, Mu Columbi is a solitary O-type star of 16 solar masses and 6.58 solar diameters. Its age calculations match more closely with Hatzaya AA and Hatzaya B. Now in the constellation Auriga, AE Aquarii is a multiple star system consisting of an O-type blue giant, a fainter star, and an A-type main sequence companion. The age of AE Aquarii has not been measured. The star illuminates the nearby Flaming Star Nebula, making it appear as if AE Aquarii was on fire. Parts of the nebula, appearing like material, is trailing behind the star. Now in the constellation Aries, 53 Eritis is a solitary B-type variable star of 7.5 solar masses. Its age has not been measured. The Hatzaya system, however, remains in the Orion Nebula. It is unique in that it contains 3 high-mass stars that have different ages. An O-type giant, AA, a B-type subgiant, AB, and a B-type giant, B, where the AB star is younger than AA and B. This means that the various components of the system will not have formed at the same time and instead were captured. Also interestingly, the massive central pair of stars both produce powerful stellar winds that become a source of X-ray radiation when they collide. It is believed that, around 2.5 million years ago, 2 star systems collided somewhere in the trapezium cluster, Theta Orionis, ejecting what we know today as Mu Columbi, AE Aquarii, and 53 Eritis from the Orion Nebula, and leaving behind the Hatzaya system. Here's an estimation of what the 2 original systems were. AE Aquarii. AE Aquarii is an anomalous binary star system of a K-type main sequence star and a compactor. The 2 stars are very close together, at a distance of only 2.34 solar radii. The secondary main sequence star is tidally locked to the primary, meaning that one side always faces the compactor. Bizarrely, AE Aquarii A is a compactor that behaves like a pulsar. It has a magnetic field which funnels accreted matter from AE Aquarii B into particle jets. Additionally, it has a very rapid rotation speed, completing a full revolution in 33.08 seconds. As if AE Aquarii wasn't weird enough already, AE Aquarii B has an unusually small amount of mass for its size and temperature. Normally a star of its mass would be class M on the main sequence. This is explained by mass loss from the secondary onto the primary. Whilst a lot of it is scattered by the rapid rotating compactor, some forms an accretion disk around AE Aquarii A that is heated to the point where X-rays are emitted. HD 226868 and Cygnus X1. One of the most interesting and famous places in space is Cygnus X1, which is a system of a compact object and a blue supergiant star called HD or HDE 226868. Ejected material from HD 226868's stellar wind forms an accretion disk around the compact object Cygnus X1, which is most likely a black hole due to mass estimates of over 10 solar masses. The mass transfer between the two components of the system produces X-ray radiation, hence the name Cygnus X1, meaning the brightest X-ray source in the constellation Cygnus. The black hole's rate of rotation has been measured to be 790 revolutions per second, which is incredibly fast for an object of its mass, and formed from a star of over 40 solar masses. High-speed particle jets have formed perpendicular to the accretion disk at the poles of the black hole. The system is somewhat similar to V838 Cygni in Cygnus X3, where mass is being transferred from a Wolf-Rayet star to a compact object, either a black hole or a neutron star, or potentially a quark star. V838 Monocerotis. V838 Monocerotis is arguably one of the most mysterious stars ever discovered. It is a system of a red supergiant and a B-type main sequence star. In 2002, the primary underwent a nova-like outburst that caused its size to increase to 1,200 to 1,570 solar diameters for a short period of time. At this point, its spectrum was measured to be somewhat similar to that of an L-type planetar, making V838 Monocerotis the first L-type supergiant or L-type hypergiant known. Intrinsic properties of V838 Monocerotis A are still disputed, some stating that the star is a massive supergiant, some stating that it is an intermediate mass star in the asymptotic giant stage. Not much is known about V838 Monocerotis B either, as it is engulfed by the dust cloud that was ejected during the eruption. There are many hypotheses for this outburst, including the helium flash of a red giant star, a merge burst during the merger of two stars, multiple large planets falling into the star, or a thermonuclear explosion akin to Eta Carinae in a massive star. Eta Carinae and the Homunculus Nebula. The Eta Carinae system is home to two hot massive stars. The primary is a violent variable blue hypergiant or a luminous blue variable, LBV, and the secondary is a blue giant. Both stars are many times more massive than the Sun. Primary is one of the most massive stars known, and rotate at 90% of their critical velocity, meaning that the stars are oblate in shape. The two stars orbit in relatively close proximity, 15.4 astronomical units, and their powerful stellar winds collide to create vast cloud structures. In December 1837, the primary blew off 30 solar masses of material in a colossal coronal mass ejection that has been termed the Great Eruption, an event that created the Homunculus Nebula. V76 Centauri. If you want big, then you go to V766 Centauri. It contains a contact binary of an orange hypergiant and an orange supergiant, and a blue supergiant. The contact binary is designated V766 Centauri A, a 67 solar mass orange hypergiant that is currently cooling and expanding, exchanging mass with a smaller intermediate mass supergiant about one-third the size. It is expected that the secondary has become distorted by the mass of the primary. V766 Centauri AA is also the 10th largest known star, at 1,315 times the size of the Sun, and the second largest orange hypergiant behind the M to G type variable star RW Cepheid. The system also contains a third star of class B. It is a massive supergiant or hypergiant, and a suspected luminous blue variable, potentially making it more evolved than V766 Centauri AA. The future of this system likely holds a stellar merger event, at least 2 core collapse supernovae, and perhaps multiple large-scale coronal mass ejections. Alright, so if you enjoyed the video, don't forget to click the like button, because that's what the like button's for. Comment if you want to comment, share if you want to share, and please, if you like my videos, subscribe. That would be great.